Hi, everyone. We're gonna kick off the lazy evaluation workshop. It's going to be done by Andres, who's one of the partners of WelpTyped, obviously one of the oldest Haskell consultancies around. They've also been a core collaborator for ZuriHack in all the years that ZuriHack has existed. And so we're very grateful for them to continue providing us with excellent courses. So yeah, let's give a short applause for Andres, and then let's get started.
Yeah, thank you very much, Jasper, and thank you very much to all of you for being here. I mean, I know it's quite a commitment, 3 hours, let's see. I'll try to do a break at some point in between. So today I'm going to talk about lazy evaluation, but before we do that, I will want to say a few words of introduction, just so that you know a little bit more about WelpTyped if you haven't heard about it before. So we're a Haskell consultancy company. We exist for quite a long time, considering sort of the Haskell time scale. We are currently slightly more than 20 people. And we're working primarily for companies that are also using Haskell, right? And then we're helping them with their projects by consulting, advising, training, and developing. And a large part of what we're doing is also sort of general GHC and tooling maintenance, but we do these other things as well. And training has always been and is a major part of what we're doing as well. We are rarely at the moment doing sort of public, free, open to all courses, but we are doing at all times sort of on-request, on-demand courses, both on-site and remote. So if that's something that interests you or your company, that is also always something that you can ask us about. So Adam, another partner at WelpTyped, already said it in the beginning. So one aspect that we're doing at WelpTyped is we have a strong GHC team of GHC developers, and they're just trying to generally help with the development, with the release management, with the bug fixing, with coordinating all the other volunteer efforts. And that costs quite a bit of time and energy, and relies on the fact that we have a number of very cool companies that are sponsoring these efforts. But it is something where we could always use more help. And Adam has been writing a blog post in November last year explaining this all a little bit further. But if you are working for a company where you think they might actually be willing to help GHC development up to an extent, we would be very interested to hear from you. As to me, I'm using Haskell since I was a student in Constance. In 1997 was my first contact with Haskell. So before Haskell 98, the first Haskell version I've been using was Haskell 1.4, which was the versioning scheme before then. That basically convinced me to switch from mathematics to computer science. So that's why I then went to Utrecht in the Netherlands and did a PhD there on Haskell. And yeah, I've been at WelpTyped now for significantly more than 10 years already. And I'm currently living in Germany, in Regensburg. There are two other things that I briefly want to point out that I'm involved in. One has nothing to do with WelpTyped. It's an initiative of the Haskell Foundation. That's the Haskell Interlude podcast. So that's we are interviewing people from the Haskell community, and we're putting podcasts out roughly, well, the goal is roughly every 2 weeks. And I'm one of the hosts. So if you haven't heard about it before, you should check it out. I think it's quite interesting. But also, for example, if you just want to suggest yourself as a possible guest or nominate someone else, you can talk to me about it. And another thing that we have recently started at WelpTyped is that we are now roughly every 14 days, we put out a live-streamed YouTube episode of roughly half an hour length on various Haskell-related topics. So that is not, I'm talking to my colleague Etzko about stuff that interests us. And some of the episodes are very introductory, and others are more advanced. But Yeah, I think it's rather interesting, but since it's still rather new, you may not know about it. If you want to check it out, the next episode is going to happen on the upcoming Wednesday, and that's not entirely a coincidence. It's actually related to this lecture because I've been preparing stuff in this direction anyway. It's not sort of redundant, but it may be a good addendum if you've already been listening to me here. Okay, so this repository at the moment is empty but should exist. I've been working on my slides until the last moment. I haven't uploaded them yet, but I will put them there after the presentation, and I will also put the code samples that we are discussing there after the presentation. Okay, so this concludes all the preparatory stuff, so let's talk about what we're actually going to do. So the plan is to look at relatively simple programs. The point is that lazy evaluation, you can see it as an advantage and as a disadvantage, but you can create quite tricky examples with very few tokens. And so even looking at small examples can be a challenge. But it also means that you can illustrate a lot of the concepts without having a lot of extra overhead. And that's the goal here, really, to build an intuition, to explain at the hand of certain examples what kind of issues are arising. And if you understand the concepts well, I would argue that it also becomes easier to work with larger code samples and larger code bases. And in particular, I believe that if you are looking at sort of the performance pitfalls for lazy evaluation, that a large fraction of them is falling into a few common classes or are instances of a few common patterns that are good to know about. Because the best space leak, in a way, is the one that you never write in the first place. Then you don't even have to worry about debugging and fixing. So if you write your code in such a way that it just performs well from the beginning, that's great, right? And if you can avoid a number of common pitfalls or at least be alert when you see certain patterns occurring that something might be off, that's already good. What we're not going to do is not trying to be exhaustive. Actually, I myself, I had high goals. I was hoping I could do this and this and this as well, and then my slides grew and grew, and I thought I had to cut some things out. There are lots of interesting topics related to laziness that I unfortunately can't cover. We're also not going to look very much into the GHC internal side of this. So the whole point is, that's in a way, I guess, a feature and not a bug of this talk. The idea is really that we are trying to explain how to reason about laziness without having to go all the way to the compiler. Of course, it's still interesting to look at what GHC is doing, but it's a different topic. And then what we're also not going to do is to look at really large code bases and debugging and trying to figure out where the potential space leaks are coming from. So that's, again, a different story. But we have been doing talks about that as well, and we will certainly also be doing talks about that again. Okay, so I'm going to introduce the concepts, but from now on, I would invite you to always interrupt me if you have any questions, and in particular also point out mistakes that I will certainly be making myself immediately. And if you have short questions, just ask them. I will try to repeat. If you have a long question, you can get a microphone to ask that. Okay? So what is lazy evaluation? I guess I could already ask that to you, but for the time being, I'm going to try to give an informal answer myself. So the general idea, right, is to evaluate as little as possible and sort of just in time. Right, so you try to delay evaluation of stuff until you really, really need it. Of course, the question is, what does need actually mean? But we'll get to that. And there is a second aspect of it, and that is to share computation results if you need them multiple times. Right, so the idea is that you never want to duplicate work. Right? If you have a certain computation and it can be shared, then it should be shared. That also sometimes leads to problems, but in general, it sounds like a good idea, right? Saving work. Let's also get out of the way up front roughly what a space leak is, because it's a term you hear often about. That is generally just a situation in which the memory is retained by the program for an unexpectedly long time, right? So you would, like, memory is used all the time in Haskell. That's just the way that Haskell works. You can hardly write any code without allocating a whole lot of memory. But fortunately, a lot of that allocated memory is short-lived and can be freed almost immediately again. And that's fine, right? But if it cannot be freed and you use more and more memory over time, then you can end up in a situation that is called a space leak, in particular if you had a different expectation. I mean, sometimes you have programs that are expected to use a certain amount of space, but if it happens in a situation where you're not expecting it at all, then it's bad, right? And then it can lead to real problems. Okay, so the next question, that's basically a follow-up question from this what is lazy evaluation, evaluate as little as possible informal explanation, is like, why do we ever evaluate anything at all? Wouldn't it be, wouldn't it be sort of the logical culmination of the idea of lazy evaluation to just not do anything and say that that's clearly the most lazy thing we can do. So why do we start, right? And the answer to that is there is usually some initial question that is being asked, some initial demand, and it's actually easier to explain, say, from a GHCI perspective. If you're typing in an expression into GHCI, right, the goal is to print the result, right? And that is the one thing that you want to do. And that is placing a certain amount of demand on a certain result, namely the result of the expression that you're trying to evaluate. And then you're trying to do exactly that, what is necessary to achieve that result, and propagate that initial demand that you want to print the result to whatever is needed in order to come up with that, right? Similarly, if you have an actual Haskell application, you have a main somewhere, right? And that is an I/O action, but that I/O action, that actually wants to be executed, right? And so that creates initial demand, and that propagates. But so there is some initial source of demand, and then things are propagated. And how are they propagated, right? There are some primitives that need a certain amount of evaluation. So if you look at it, for example, integer addition is an interesting function because you can only compute the sum of two integers if you know both the integers, right? So if you want to have the result of an integer addition, you will have to sooner or later evaluate both the left and the right argument. But in general, by far the most cases in which propagation of demand happens in Haskell is by pattern matching. Right? Integers are sort of a primitive base type, and they follow slightly special rules, and plus is in the end also a primitive function. But if you look at normal Haskell data types and functions, then almost all Haskell data types are defined using the data construct. They have multiple constructors. The constructors have arguments. And then you define functions that, in the end, if you go all the way down through the expansion and the recursions and the higher order functions, but in the end, that boils down to doing pattern matching at certain points. And pattern matching requires you to know, is something constructed using this constructor or that constructor. And in order to answer a question like that, you actually need to evaluate. Right? So it's basically primarily case on pattern matching constructs that are doing this demand propagation throughout code. Okay, let's leave it at that for sort of the informal introduction and setting the scene and start looking at examples, unless there are already questions. Perhaps there are already questions. No? Okay. Good. First example is very simple. We are going to look at the null function. Right, and this also gives you a little bit of a taste for the kind of questions we're now going to ask throughout this session all the time. Right, so we have a simple function, example 1, that goes from int to bool. It calls null. Null is a function that checks whether a list is empty on the list that is 0.n. right? And now we can parameterize that over n. And basically, if I'm asking how much space does this use in terms of n, that is, of course, like sort of an ill-defined question, because I'm not running, like as long as I'm not running this function, nothing happens, right? But let's assume I would, say, type in example 1000 on GHCI and hit return, or let's assume I write a little main program, which I actually have. So I have this piece of code here, which has all the examples from the lecture, and here I have a very primitive wrapper where I'm just reading from the command line an argument and read it as an integer, and then I'm calling one of these example functions. So if I compile this piece of code and then run that with different values for n, how much space does it take in relation to n? What do you think? Constant. Okay. So what would even be another, like what would be possibly the only other plausible answer that could be considered? Linear, right? I mean, because you could ask, like, I mean, is this list, is this going to be realized in memory? Yes or no? Okay. So constant is the assumption. So now there are different ways of verifying that assumption. One is sort of the one that really counts, because the one that really counts is to run it. Right, I mean, you can reason all you want, but if the computer in the end takes a long time anyway, it doesn't help. Right, so that is something we should learn how to do, right, and how to run. But the other thing is we can reason about it. So let's see. Let me briefly go back to my talk. So if we want to reason about it, we have to look at the definitions, right? And I will try to define the functions on my own here so that we have clear and relatively simple definitions. That is actually a problem of this reasoning approach, that if you go and look at GHC's real definitions, they're often quite a bit more convoluted. I mean, if only because, I mean, there are additional like ways in which this is written so that it is particularly amenable to rewrite rules or there are extra performance optimizations. I think for null, I haven't actually checked, but for null, probably you're getting pretty close. I mean, there's not much else you can do there, but it's something to keep in mind. At the same time, though, most functions that, even like if functions that live in base, have something like a specification, right? So there is an idealized version that is written down in the Haskell report or somewhere else that says, like, even if you have a more efficient implementation, it should in principle behave like that. And that also usually entails, in particular, with respect to laziness. So, it might be that GHC behaves differently from what you end up with your own definition, but at least that then already hints at something that is going strangely, okay? And so we also need to look at this list generation syntax, right, 0.n. And that's actually a syntactic sugar in Haskell for enum from 2. And here I'm clearly using a different definition than GHC uses internally, because that is much more optimized. But I'm nevertheless going to go with this relatively simple definition on integers, where we're just checking whether the lower bound is greater than the upper bound. If so, we're producing the empty list. Otherwise, we're producing a list that starts with L, and then we recurse on enum from to L plus 1 and U. Okay? Good, so if we have done that, then we can do equational reasoning. And actually, I'm very grateful to Alexis and also to Simon yesterday. In both their talks, they have made a case for reasoning about programs by doing these kinds of transformations and rewriting rules and so on. So that is a good introduction to this. So, so let's just assume, let's just see what happens if we set n to be 2, and we try to figure out what happens. So usually we proceed by rewriting, right? By reducing something that we can reduce. Now both null and enum from 2 are just functions. How do we figure out what we can reduce or how we can reduce it? Any suggestion? How do we figure out what we should do? Yes? So the suggestion is to start with enum from 2? reducing...
Place the name by the definition.
Yes. I mean, so basically, what we would have to do if we want to be really like precise, we could replace the names by the definitions. That is the suggestion. I'm not going to do that at all times because it would become very lengthy. So I'm just going to sort of do if I have a fully applied function call like enum from 2. And I have a right-hand side, I'm just going to directly replace the left-hand side with the right-hand side. I think that's a good proxy in general, right? So, and for enum from 2, we can actually do this, right? Because we can do it right now, because we have 0 and 2, and we have an equation there that tells us what that reduces to. Whereas for null, right, even though we have a call to null here, we cannot currently easily do this. Why not? Yes, because we have pattern matching, right? Because null is defined in terms of 2 equations, one for the empty list and one for the non-empty list, and we currently don't know which of the 2 equations applies, right? So this is where pattern matching driving evaluation already comes into play, right? Okay, so there's basically only one thing here we can do. Okay, so we can reduce enum from 2, and then we get this, all right? And it's important that we just do replacement, that we don't do any tempting evaluations already, because we want to be very precise. So in particular, I'm writing enum from 2 of 0 plus 1 and 2 on the right-hand side. I'm not writing enum from 2 of 1 and 2 there, right? Okay, so now, what next? What can we do? Sorry? Yeah, check the if condition is the suggestion. Right, so the point is we can still not reduce null, because we've already established that we can only reduce null if we know what the list it is, and we don't know that, right? So we have to do some progress with this if, and if is a little bit of a special construct, although you could define a function that behaves just like if. But the point is, you can only reduce if you know what the condition is. It's a form of pattern matching, actually. You can treat if as being a function that does a pattern match on the condition, and depending on whether that condition evaluates to false or true, which are the 2 constructors, yeah, it makes a choice. So again, it's a form of pattern matching that is driving the evaluation here, and we have to figure out what 0 is greater than 2 reduces to. So that's the next thing that we're going to do. Now this is more or less primitive, so we're just going to assume that works, right? And says false. Okay, so I'm not going to look at like how greater on integers is actually defined, but we're assuming that works in constant time. That's an assumption that goes into it here. And now, basically the definition of if comes into play, and we can reduce if false to go to the else condition, right? So we get this. Okay, and at this point, now we actually have, I think not for the first time, but perhaps for the most significant time, we have multiple choices. What choices do we have?
That's enough information to evaluate null.
Right, so that's the first very important observation, and that is actually what we are going to do. Right? This is enough information to reduce null, because null had these 2 equations, one for the empty list and one for the non-empty list. But if you look at the one for the non-empty list, it says underscore cons underscore. So there's nothing we additionally need to know for the arguments to the cons, and we know here that it is a cons. So that's enough to say false. But it's one of the options. I mean, it is the one that we are doing, but what are the other options that we would have?
Evaluating 0 plus 1.
Evaluating 0 plus 1, and there is yet another option that we would have.
Enum from 2.
Evaluate enum from 2. Yes, exactly. Okay. So let's skip this for the time being and just go to this, because we're discussing it right now. So there are these 3 possible choices for reducing the expression in this particular sub-expression, right? So, and these are all, Alexis already said this, these are called redexes, for short for reducible expression. And in general, if you have an expression and you're doing this kind of equational reasoning, there will be multiple choices. Okay? And if there is choice, then we have to know how to make that choice. Do we randomly pick, or do we, I don't know, follow a certain strategy, and if so, what is that strategy?
Does it matter? Isn't it congruent?
That's a very good question. The question is, does it matter? And isn't it, I think you meant confluent, right? Yeah. So, and that's a very good point. So, it does matter. It does matter for two things. So, it is confluent in the sense that if a reduction sequence arrives at a result, right, then that result will always be the same, right? But the number of steps you take to get there may vary depending on the strategy, and it may even be varying insofar that in some strategies you may have infinite reduction sequences that never lead to a result, and in others you may not. So basically, yeah, it does matter, mostly for efficiency and for the number of steps you need, but it also may matter whether you get a result at all or not. Right? So because it may loop. But you will never get, like, one reduction sequence leads to 1 and another reduction sequence leads to 2. That's fortunately not that. Okay, so, so it does matter to an extent. So we still have to answer what's the strategy?
Top-down.
Top-down is perhaps one way to put it. I mean, so the general thing is you try to pick the outermost regex, right? So the syntactically widest, right? So the one, or if you draw the syntax tree, the one that is sort of most at the top, that is spanning the largest part of the tree. So here this is the null, right? So the other two are clearly contained within, so we would pick this one. That is the one that corresponds to lazy evaluation, or more generally to what is called call by name or call by need, which are both variants. Call by need is more or less precisely lazy evaluation. Call by name is sort of a term that is often being used for picking the same reduction strategy but not caring about sharing quite as much. Okay? So that's the general strategy. We pick the outermost regex whenever we can. And that is also the thing that we should apply. Okay. So there are two things now. That was our reduction sequence, and we've been following this outermost reduction strategy. So there are two things to still add. One is that if we have been making the assumption that n is equal to 2, but if you look at the reduction sequence, where does the 2 actually come into play? Right? The only point where the 2 is really important is when computing 0 is greater than 2 and evaluating that to false. And it would work for any number that is greater than 0, right? And so and in particular, I mean, the number of steps is not at all dependent on the 2. Right? So if we had 4 or 5, we could write exactly the same reduction sequence. So this gives us a pretty strong hint that this program runs in constant space and time. Right? I mean, the number of steps doesn't actually give you an indication of space. It gives you an indication of time, even though not a necessarily very reliable one, but certainly a sort of an approximate notion of time. What is it that gives you an indication of space? Yes? The size of the expressions, yes. So I mean, of course, if it's kind of, if you say independently of n, we have exactly the same reduction sequence, then also the size of the expressions doesn't change, right? But if you're seeing, even for a single n, if you see that, I don't know, the number somehow, right, determines the sort of the sizes of the sub-expressions or something, then that is something to worry about, right? And that's the point. I mean, like, what is sort of the maximum size of sub-expression that we're going through is often going to be an interesting question. Okay, all right. So that was the reasoning side. Now let's look at the measuring side, because that is also important, right? So for that, the simplest, by far the simplest way, and you would be surprised how often I do that even in real life, even for large programs, is just to measure. right? I mean, it is harder if you have multiple things interfering with each other, but just to measure on a very superficial level and just ask GHC to report some statistics about memory use in particular. Time use is not the thing that we're most interested in today, but before you jump to profiling and GHC debug or whatnot, I mean, the easiest thing you can do is just to look how much space does this program really take, and in particular, if you can vary the problem size, that's like we can do here, that's very interesting. So let's do this, right? So let's do GHC, and I'm going to say -0. I'm going to try to be explicit about the optimization level, but normally, right, if GHC is not totally wrong, we would hope that if you do optimizations on, you will get better. Right, not worse. So if you can establish that a program runs reasonably well without optimizations, that's good, right? Because then, like, with optimizations, it will hopefully only get better. So very often today, we'll just look at unoptimized GHC, and specifically not look at whether, like, the optimizer can make a qualitative difference. There's one or two situations where I will point out that there are differences, but we'll see this. Okay, so we are going to compile this, all examples, and oh yeah, so perhaps I should, because I have done this before, just to be sure, like, I mean, force recompilation, right? So this is a flag for those who don't know. That just tells GHC to abandon sort of the clever checking whether any work needs to be done, to be less lazy, right? To recompile even if GHC thinks it's not needed, and then I'm going to call the code, and I'm going to pass an argument because I need to pass an argument. So let's start modest with 1,000, and then I'm going to pass a runtime system flag. So this is every Haskell program that you're compiling accepts these flags. Not all of them, but in principle, the parsing of these flags is done by the runtime system, right? And the only one we're going to look at today, but there are quite a few actually, which are helpful and which can tweak things. The only one we're going to look at today is this -s or -s flag, which gives you quite a bit of statistics. Actually, potentially too much, right? Because you have to know where to look. And there's basically only one line we're going to be interested in today. Which one is that? I mean, that's for people who already know. Because if you don't, there's probably not a good... The first one, yeah, so that you might think that. But that is, we'll see that, I mean, so let's actually see. If we increase this, the first one goes up a bit, changes a bit, but yeah, let's see. But I mean, in general, I mean, this is a special case, right? Because we have constant time, constant space. The work is really more or less essential. But in nearly all programs, program bytes allocated in the heap, that is sort of over the whole program time, how many allocations have happened, right? So there are plenty of programs that run in constant space as we view it, that actually allocate quite a lot. Because, as I said initially, very often you allocate and immediately free again, and that is generally fine. What you're really interested in is what is the maximum amount of memory that the program takes at a single point in time. And that is given by maximum residency. Right, so that's the one that you're mostly interested in. And now there is a certain minimum amount that you'll never get under, and that is exactly these 44,328 in this case. I guess it can vary per GHC version or something, or even per architecture, I don't exactly know, but that's something to be aware of. You cannot be satisfied by, like, saying, let's try this on 1, and let's try this on 10. Oh, that's an order of magnitude more. Both is 44K. Great, done. Constant space. That's not enough, right? So you have to be more doubtful. In particular, if you see this number, a number in this size, is like basically saying, okay, so it's probably just not exceeded the minimum amount that it always uses. But here, even if I do a relatively large numbers, in particular because we know that we have a constant time program, it always prints false, and the maximum residency does not change, right? So that's good. So so this one works, or well, works nicely, like as nice as it could. Any questions so far? What about 0? Okay. What were you expecting?
Just like 1 errors.
What about -1? I mean, that's the more interesting question. I don't even know whether that, do I have to do something like this? I don't know. Yeah, so this is where the command line parsing gets problematic, so I think I have to prevent it being, I have to probably do something like this, right? Yeah. It just works? Okay. Fair enough. Yeah, right, okay, because I'm not using any command line parsing library on the Haskell side. Okay, no, but it still says pattern match, oh yeah, no, it says rightly so, it says pattern match failure in the no, why does it say pattern match failure?
That's a good question.
It does not see it as one argument, apparently. Anyway, okay, so let's not go there. I think this is beside the point of the talk, even though it's a curious analysis. But let's go to other things. So we're not going to consider negative numbers very much today. Okay, let's go back to the talk. So, any other questions at this point? No? All good? Okay, so let's look again at this question: why does anything happen at all? Let's try to go back to this. Like, where's the demand coming from, and how is it propagated? Right? We want to print the result of the resulting bool. Right? Both in the main program there is a print. And even also if we would like just type it into GACI, in order to print it, we have to know what the actual bool is, whether it's true or false. That is a precondition to producing the string true or false on screen. So therefore, we have to evaluate the call to null, and then it's the pattern match on the null that propagates demand, which we've already answered, right? Okay, so this kind of pattern matching, again, that is the thing that usually propagates demand. So now the next, like this is probably something that most of you will know, but I mean, I'm surprised how often, even for people who have been using Haskell for quite a while, they have to remind themselves of this, that just because you evaluate something doesn't determine that you evaluate it all the way, right? So, okay, we have to evaluate the argument to null in order to be able to reduce null, but that doesn't mean that we evaluate the list all the way, right? That is very much a part of what we've already established. But how much reduction do we do, right? And here we have a situation where revealing the top-level constructor is sufficient to reduce null. And in general, that is the most fundamental case distinction you have in Haskell. You have pattern matching. And if you have any kind of meaningful pattern matching at all, it will distinguish at least on the top-level constructor, right? And that means that whenever you want to do any evaluation, it makes sense to evaluate until you know the top-level constructor of the result. Because before you have determined what the top-level constructor of the result is, you won't be able to make any progress that you couldn't already make in the reduction, right? But you also don't want to do more, because if you were doing more in this situation, like where we have 0 cons enum from to 0 plus 1, 2, we could easily start evaluating the entire list, and that is exactly what we don't want, right? So we want to stop at the time that you have revealed the top-level constructor. And that is where this notion of weak-hat normal form comes from. Why? I mean, the name is strange, okay? But that's why the concept makes sense, because a weak-hat normal form is if an expression is a constructor application or a lambda. Like if it's a function, you like treat the form in which is a lambda expression as sort of the sufficiently reduced form, because then you know that it expects an argument and then you can apply it, right? But an expression could still be in a different form, like an application of other functions that only after a couple of reduction steps reduces to a lambda. So for functions, this applies as well. But that's basically the case. You evaluate up until the top-level constructor, and the reason why this is an interesting notion is exactly that might enable you to make more progress that you couldn't make before. And you don't want to do more than that because you want to be lazy, right? You don't want to do anything that you don't yet know you will need, okay? Okay, so now let's do, just make sure that everybody understands this, right? So null repeat 1, what will it do? False. Just false, right? Because, I mean, repeat 1 is a function that will eventually reduce to something like 1 cons repeat 1, and then we can reduce to false, right? Constant space, constant time, false. Null of undefined, yeah, will crash, right? Because what happens if we try to reduce undefined? We crash. And why do we reduce undefined here? Well, because null is defined in terms of pattern matching. Right? And therefore we have to reduce undefined to weaker normal form. That's triggering a crash. Null of 1 cons undefined is false, right? Because we never look at the undefined. It's already in weaker normal form, we can reduce immediately. Null of undefined cons undefined is false as well, right? And then we have null of let x equals x and x. Yeah, that loops, right? Because that's another thing that can happen. And often actually in papers and in theory, that's all thrown together, right? Like looping and crashing is sort of seen as one and the same. But it's another thing that can happen, right? It's a type-correct expression that you're allowed to write in Haskell, like for a list, even though it doesn't use a list constructor, right? Let x equals x and x is type for all AA. And if you start reducing that, it is going to loop, okay? Is there a question? Oh, yes.
Regarding your definition for weak and normal form, what are things that are not constructors, like integers, for example? Is that a constructor then?
Yeah, so I mean, for types that are not like sort of data types, you have to make your own conventions. But usually, in the most common case is that then you have a type that is essentially, I often call it flat. So basically, it's like a huge enumeration type. You can view integers as a huge enumeration type, and then every individual integer is like a constructor. Obviously, you have a more efficient internal representation than that, but nevertheless, evaluation of an integer to weaker normal form just means determining that integer, right? The same for doubles or things like that, right? Good question, though. Any other questions? Good, okay. So, as an aside, I mean, I don't think it's actually so important for the rest of this talk, but it is terminology that is thrown around all the time, so I think you shouldn't leave this talk without knowing. So functions are called strict, and that is like a function in the Haskell sense, a function in one argument, right? A function is called strict if and only if they're applied to bottom, and that is exactly this what I just said, like sort of the theory paper notion of anything that crashes or loops. If applying a function to anything that crashes or loops will result in a crash or a loop. Not necessarily the same thing. Right? A function is still called strict if you apply it to something that loops, if it then crashes. A function is also called strict if you apply it to something that crashes in one way that then crashes in another way. That's the theoretical definition. This is how it's defined. So why is this a good definition, right? I mean, it's also, you can argue, but I mean, it is a good aspect of this definition is that it's a definition that is defined in terms of a function's behavior. You can talk about a function being strict simply by like observing how it behaves. You don't have to look at the code, right? So that's in that sense, it's good. Right? You don't necessarily have to know the implementation of a function. If you're given a library that you can't see the source code of, you can still figure out how strict the functions are in there simply by calling them. Right? So you can, yes?
What if I evaluate the type of a function provided with a bottom argument? Would I get bottom as the type or the original type?
So the question is, what if I apply the type of a function with bottom? But the problem is I cannot parse the question, because this is not giving a type. This is just basically an equation on the term level. If you apply the function to a crashing or looping value, right, and it says nothing about the type. But in the simplest case, undefined is a value that can have any type, so you can do that for any function, regardless of what the type of the function is. You can always try to apply it to undefined and see if it crashes. If it crashes, then it's strict.
Yeah, I was thinking about GH interactive mode. What's the type of function applied to bottom? Or
Yes.
Something which loops.
Okay, so if you're asking in GHCI, let's see. So let's start GHCI. If we're, for example, wondering whether, I don't know, what is it, null is strict, right? And we're asking for the type of this, we're still going to get bool, right? Because this is purely the type checker. The type, like, as far as the type checker is concerned, undefined is of like any type you want it to be. Null is expecting a list. That is a type correct application, and the answer you're getting is dependent on the type of null, which is in this case a bool. Does that answer the question? Okay. Yes, Far.
I was always a little bit uneasy with this definition of strictness because I was always a bit. Yeah, I was always a bit uneasy about this definition of strictness because it automatically implies that I need a language in which all types have an undefined. I don't know. Aren't they two orthogonal things? If some is lazy.
Okay. Yeah, I think it's actually a good point, and I mean, I certainly it's only an approximation of what is useful in practice, and I mean, if I just step further here, I mean, I have a couple of points which I personally think are not so great about this, and one is, which is, I think, not the point that you've just made, is that I think some of the implications of this definition might be unintuitive, but there are reasons for that. But the second is related to your point, I think. It's that it's not a very precise notion, that already, even if you have undefined in your language, it's only giving you very partial black and white information about strictness. But in practice, you need much more sophisticated and detailed information. And that in particular is relevant also if you're saying, okay, let's assume we're in a total language in the first place or something like that, and we can't even get through the type checkers, and so then what? But there are still performance implications as to in which order you're evaluating something. So I think it's a valid point. Yeah.
Thanks.
So nevertheless, let's briefly practice. Is null strict? Yes, right? I mean that's. Yeah, because and we can try this out because we can say we can actually execute this call, right? And it crashes, and that's good enough, right? And yes.
If you use the default implementation of null, it doesn't crash on. There is difference when you do undefined.
If you use the default, I mean, this is the default definition of null. Undefined plus undefined. Like this?
Yeah.
Yes. But that's okay, right?
Do this list. Evaluate this list.
Sorry.
So evaluate undefined.
Yes.
You're saying that because it evaluates
Yeah, so see, it's you have this crashes.
No, this doesn't crash. That's a very good point, actually. Do you see the square bracket there? So that's actually a very good point you're making, right? I mean, so if you want, right? Because like printing the result, right, actually typically places an enormous amount of demands on the result. You have to be very careful, right? So here the point is undefined cons undefined. So the cons constructor is not strict. Right? Because if you, I mean, first of all, it takes two arguments. So cons applied to undefined is not really anything yet anyway. But even if what many people are doing, if you're informally extending the notion of strictness to sort of multiple arguments, even cons applied to undefined and undefined, right? It actually is in weak-head normal form, and you can do stuff with it. And if you're trying to print it, the printer will start. And that's what you see, like with the square bracket. The printer will start. And only then, because it wants to print the contents of the list, it will also start evaluating, in this case, the first undefined. And that will produce the crash here. Yeah, so you have to be careful. But I think that's a good point, actually, right? But we're... But nevertheless, right? I mean, if you are in the situation of null itself, right? Here, there's really, I mean, there's nothing you can see, but there is also really nothing behind the scenes. So I mean, this is really an indication that it's strict. Okay, good. All right. What's an example of any non-strict function? Constant function. Very good. So here, const 0 is like a very simple example of a non-strict function, because we can apply it to undefined, and it gives us 0. That's a pretty good indication. I mean, the other way around is perhaps more critical, as we have now seen, right? Because if you're in a situation where you couldn't see the square bracket or don't look closely, right, you might still have to question yourself, well, is it just an artifact of the call to print that GHCI does, or is it actually because the evaluation crashes immediately? But if it gives you a value, like without any crash whatsoever on undefined, then there is no question about it. The function is not strict, right? So here is one that often tricks people. Is the identity function strict?
Yes.
I already heard both, yes and no. Like so who is in favor of yes? Who is in favor of no? Oh, this is actually pretty even. Wow, okay. So did you say no? What is your argument in favor of no?
Because we don't do anything with the variable, we only pass it further.
Yeah, but you're not applying the definition, are you? You're applying an intuition.
That's my intuition, yeah.
Yeah, intuitions can be wrong. So, so the definition is pretty clear. The definition says if we apply it to undefined, it should yield undefined, or well, bottom. But nevertheless, if we do that, right, it does, because the identity of undefined is undefined by a one-step reduction. Now, as to the intuition, I think there is a part to it which is very understandable, but it's also dangerous. So another thing that is often sort of like, and there I would say intuition is really wrong. What I often hear people saying, and you really have to be careful about that language, is this function evaluates its argument. Have you ever said that in your life? Raise your hand if you've ever said it. I have said it many, many times. Like this sentence. It's a dangerous sentence, because when does a function evaluate its argument in the first place, right? The reason why you're looking at a function at all in the Haskell lazy evaluation setting is because you're interested in its result. There would be no other reason you would even start looking at the function, right? And then the interesting question is not, does the function evaluate its argument, but does the demand that has obviously already been placed on the result, does it propagate to demand on the argument? And that is trivially true for ID. right? And that is why it makes total sense to treat ID as a strict function, because it propagates demand from result to argument. And that is also really the better notion. I know we always speak in an imprecise way, and I do it as well, and also say a function evaluates its argument, but it's really not a very meaningful notion. What you want to know is, does evaluating the result of a function trigger evaluation of its arguments, and which arguments, and how much of its arguments? That's the interesting question. Yes?
So it's not kind of like repeating demand. Can we write an analyzer that's going to look at the definition of function and will say how the demand is going?
Yes, that's a very interesting research topic. Is Sebastian in the room? No, but there is a demand analysis, right? Or strictness analysis and demand analysis is related, but you can do static analysis of functions and try to figure out how much of their arguments they are evaluating and in what way. And there are plenty of papers about this, and GHC implements one. GHC has a demand analyzer, and that is one of the things that is being used in the optimizer. And we are going to come back to, I think, one example where it plays a role. So you can do that, but it is always going to be an approximation, right? Because in the end, it's sort of an instance of the halting problem. You have arbitrary dynamic decisions that can determine whether something is needed or not. So in the general case, you cannot give a precise answer, but in many cases you can be pretty close, or you can determine an upper or a lower bound of demand. Yeah. Okay.
We said that with null, for example.
Yeah.
It is strict because it maps bottom to bottom,
Uh-huh.
but it does not map a list of bottom to bottom.
So, is there a name for functions which, imprecise speaking, evaluate everything? Because null does not do that, right?
I think there are probably papers who try to define names for all this. But I am not very familiar with the sort of the standard naming scheme there. But in general, you're right. I mean, as I said, the pure notion whether something is strict or not is too imprecise. So what we often use in Haskell terms is sort of relatively informal notions, such as spine strictness, in particular if you have a data structure that has elements. There is often an interesting difference between evaluating parts of the data structure that are not the elements and evaluating everything, or sort of fully strictness, or just perhaps more precise, evaluates its argument to normal form rather than weak at normal form. Now I've said it evaluates its argument, but triggering demand on the result causes evaluation of an argument to normal form, where normal form actually means evaluate everything all the way down, right? That is something I should also have said. Weak at normal form is this evaluate far enough so that the top is a constructor application. Normal form means all the way down. That is certainly more precise, but it becomes very complicated, right? Because there are actually pretty many. It's something I thought about. I decided against it, but if you want nice little exercises that are already relatively mind-boggling, try to answer how many different values are there in Haskell of type pair of bool and bool or something. Relatively simple, right? But that's already complicated. Or how many lists are there where the length function? No, I have to phrase that precisely. How many lists are there where length of take 3 of the list returns 3, or something like that, right? So, just because undefined can appear in so many different places, right? And it's sort of the simple notion that a Boolean has 2 values, and a pair of Boolean, because it's a pair, has 2 times 2, therefore 4 values. That's not at all the case, and that's actually one of the points why, like people, for example, like Bob Harper, are not very fond of laziness, because all these notions break down or become much more complicated, right? So in eagerly evaluated languages, you typically can say you may have an undefined, but it's always just added as one extra element. It's not sort of appearing inside of the value. So then a pair of two booleans notionally has either 4 values or 5, depending on whether you include undefined or not. But it doesn't get any more complicated than that. But in Haskell, it's like you can have undefined at the top level, right? And you can have undefined in the first component, undefined in the second component, and so on and so forth. Yes. You want a micro, or should I repeat?
I can. What about, is undefined itself strict?
Okay, so the question is undefined itself strict? So I think there are 2 answers to this. I mean, you have to look at the definition of strictness is for a function, right? So you have to look at undefined as a function. But it's fine, you can look as undefined as a function because it can have any type you want, and then you just try, right? I mean, but...
And it just says undefined.
Yes, exactly.
But is this the undefined as a function, or is undefined as the pattern? I mean,
No, yeah, but that's the other example I have here on my slide. So you're saying it does say undefined. So yeah, I would say then you're done already, right? If undefined like crashes, then according to the definition it's strict. But the other point, and that is the perhaps like even more unintuitive point about the definition of strictness, is that which undefined doesn't matter. Right, and that is deliberately chosen. And you may think that this is just like the researchers and so on and so forth. But actually, I think it was your question about the demand analysis. So if you look at the Haskell standard, it basically the only thing that it prescribes is that Haskell adheres to what's called non-strict semantics. And what this means, without going into a lot extra details, is that it should give you the same results as sort of lazy evaluation in particular does, but it can do tricky little things in optimizations, and it is actually allowed to replace bottom by bottom. I mean, if there are different notions of undefined. And that is something that happens. There are examples you can very easily trigger. We won't have the time, I'm afraid, but perhaps like offline after the talk I can show you. You can easily trigger where you get 1 error by GHC if you compile with O0, and you get a different error if you compile with O1, because the demand analyzer rearranges evaluation order and says, bottom is bottom, I don't care, right? And that's okay, according to the standard. Like if it can determine that it would crash anyway, right, then it's allowed to crash in a different way. That is fine. And that is why this definition also makes sense, because it enables demand analyzers to work. Otherwise, there is not much you could use them for. Because you basically must be allowed to make things more strict. That's the main point why you want demand analyzers, to make things more strict, like automatically. But that can sometimes, then if these computations are computations that can contain undefineds or so, it can change the order in which certain error calls or whatnot are being executed, right? And so if you wouldn't allow this reordering, there is very, very little safe optimization you could still be doing, at least in a partial language as Haskell. There was another question somewhere, yeah.
I would say that undefined as a function is non-strict because undefined applied to 0 would be.
Oh, no, the if and only, sorry, so the point was, the definition said if and only if, but I mean, maybe I made a mistake, but I think the if and only if scopes differently, right? So if this is misunderstandable, then I'm sorry for that. I don't mean that only undefined equals undefined. That is not what I mean. I mean that a function is called strict exactly if the application to undefined yields undefined, right? And if it yields anything else, then it is not called strict. So sorry. I mean, but a function may return undefined, like const undefined is also strict, right? I mean, that's, yeah. Okay. Now, how are we doing? Like, I think there are two modes I can think about. One would be, like we started at roughly an hour ago, one would be to go on to roughly 1.5 hours and then do a break of 15 minutes or something like that. Or the other would be to try to have two smaller, like 10-minute breaks, and then the first one could be now. Well, which of the two would you prefer? Who's in favor of breaking now? Who's in favor of breaking later? That's more, I'm afraid, sorry. I'll go with the majority here. Okay. Good, okay, so let's look at a second example. Okay, so just to give you a little bit of an indication, obviously the first example we established a lot of stuff, so that was very long. Now probably the next 2 or 3 are getting a little bit shorter, and then it becomes more difficult again. Right, okay, was there more questions? No, okay, just, okay. So let's look at a different example. Null, still null, but null defined in a different way. We're going to use a definition of null that is looking like this. Null via equality, it's called. And we're taking a list, and we're comparing that list with the empty list. Okay? And then we're doing the same thing again. What's the verdict? I guess we have already established in the context of the first example that there are only 2 viable answers, constant space and linear space. So let's do a vote again. Who is in favor of constant space? Who is in favor of linear space? Okay, so there's a majority for constant space. Well, we can do our things again, right? Shall we measure? We can measure. Example 2. So that is this one, just so that it's believable. Let's compile with 0. Where is my call? And let's run. Let's be bold. Right, so this is like, even for a relatively large number, still looking pretty good in terms of maximum residency. So yeah, so constant space is correct here, but why? Right? I mean, you could think that comparing lists for equality requires evaluating the lists, right? How else? Sorry?
The point is how equals.
How equals is defined? Yes, of course. As always, we have to look at the definition. Yes, there's also a question.
Yeah, I think you need to... Oh, no, you go on.
Okay, fair enough. But it's a good point. I mean, of course, you have to look at how equals is defined. But there is no real discussion about how equality on lists is defined. And I think this is actually, I really looked up the instance definition in the THC code base. So this is like modulo layout and naming is exactly the way that the instance is defined. So it's defined by pattern matching. There are 2 cases. Nil equals nil is true. Cons equals cons reduces to another 2 equalities. And any other combination is false. So now we just do the same thing, right? We have only one way to reduce this because, well, actually, no, to be completely honest, we have 2 ways. Because null via equality is now no longer defined in terms of pattern matching. So we can actually reduce null via equality to its definition. There is no pattern matching, so we get this. So I was getting ahead of myself, right? But now we cannot reduce equality because equality is defined by pattern matching and there are pattern matches on both arguments. And so we cannot reduce this if we don't know the top-level constructor of both arguments. Right, so we have to reduce enum from 2, we get this, and that's something we've already seen. So 0 greater 2 reduces to false, then this reduces to this, and now we can reduce equality. Right, and even though it's an infix operator, and that may hide it a little bit, that is the outermost regex, right? And so we know the left-hand side is cons, the right-hand side is nil, and if we look at the definition again, that allows us to get through, because the first case clearly doesn't match, the second case clearly doesn't match, so we end up in the catch-all case, so we are false. Okay? And therefore, still constant space, constant time. All good? Great. This is nothing to do, I guess, because we just established that they are more or less equally efficient. Nothing to do with the laziness or with the efficiency. But which of the two definitions of null is better? Just as an interesting side question.
They're equivalent?
So there is quite a few people who say equivalent doesn't matter. I would say it does matter. Does anybody see why it matters?
Oh, 0?
Yeah, okay, so you could probably, no, I'm not trying to make an efficiency argument that there is one indirection more and that might make him, I mean, fair enough, I mean, I don't know, to be honest, but I would guess it really does not matter at all. That would be my, for efficiency. But there is a non-efficiency argument. Exactly, I mean, I have sneakily avoided giving a type signature for this one. But the type of this one is unnecessarily restrictive, right? Because if you infer it, it requires the arguments of the list to have an equality constraint. And that is because the whole type system, of course, is static and doesn't take into account that you're comparing with the empty list and will never end up actually calling an equality check on the elements. And but why should you be disallowed of checking the emptiness of lists that contain functions or something like that, right? So this is not a great definition for that reason. Okay, but that's a completely different argument. But again, something, I mean, for beginning Haskellers may sometimes feel more natural to define it this way, but it is something to keep in mind sometimes, that you don't want to introduce unnecessary constraints. Certainly not if you want to do a general function, right? If you do it in a specific instance, like you have a concrete list and compare it with the empty list, okay, right? But if you write a general library function, you shouldn't give it unnecessarily restricted types. Okay, so next example. So this one was fast, right, compared to the first. Next example is self-equality. So the idea is we have a function self-equal, and here, yeah, we admit we have an EQA constraint, and we are taking an x, and we're comparing it with itself, right? So that should ideally, like if the equality instance makes some sense, should always return true, but we are interested in efficiency here, not about like particularly compelling examples. So this, like if we apply self-equal to a list again from 0.n, what's the space behavior? I guess again the question is constant or linear. Let's do it again. Who is in favor of constant? Well, that's getting fewer. Who is in favor of linear? Ah, good, yeah. I already tricked most of you. So we can measure, once again. I mean, I must admit, I will be totally transparent. I was looking for an example for something different. I came up with this example, and it behaved differently than I thought. And I thought, okay, let's move it to a different point in the presentation. Let's see. So example 3 is this. So let's change up here to example 3. Let's recompile. Let's run. Let's still be perhaps a little bit less bold. So one thing changes. Right? Can you see that before we had bytes allocated in the heap always remain a relatively small number, right? So that changes. Also because self-equal, this check, I mean, it actually has to compare the two lists, right? So this will do non-constant work. I mean, we are now to the realm of linear time. Before we have been constant space, constant time, right? But now we clearly are a linear time, and there is actually allocation going on during that time, but it doesn't affect the maximum residency, right? It's all allocation that can be freed immediately again. And we'll see, you also see that if you look further down, there's this garbage collector statistics. You see that there are far higher numbers of garbage collections than we've seen before, right? I don't want to talk too much about this, but there's an indication of more work going on. But maximum residency, which is the relevant line, that's staying pretty well. And also, the garbage collector is actually pretty efficient in situations like this, right? If you always use little memory and allocate and free almost quick, that's the main use case that the GHC garbage collector is optimized for. That short-lived data that can almost immediately be deallocated again. So this productivity count, which is basically giving you an indication for how much of my time is my program actually spending useful work as opposed to doing just garbage collections, is still pretty high, right? So that's good. Okay, but it's constant space. So why is it constant space, and why did so many of you think that it isn't, right? I mean, it's becoming more tricky. It's significantly more tricky than the other examples, admittedly. So because sharing comes into play, right? Because we have a situation now. Before we have been not perhaps exactly precise, because variables have only ever been used once. But now we have self-equal x equals x equals x. So x is used twice on the right-hand side of self-equal. And so now for our on-paper or on-slide, on-screen reductions, we have to be careful how we're going to deal with that, with this notion of sharing. Implementation-wise, right, so as a very rough approximation, right, these are like suspended computations that are often called chunks, are allocated on the heap, right, and then when they are being evaluated, right, or when they're shared, you have multiple pointers to this same suspended computation. When they're being evaluated the first time, they're effectively updated on the heap in place. So if something else looks at them later, it will find, oh yeah, it's already been updated. So it's implemented by a form of mutation, actually more or less the only form of mutation that you have in Haskell, right? Because most things are just like not destructively updated, but just freshly allocated. But this form of mutation happens, and it's benign in the sense that it is just giving you sharing. So if you don't want to reason about a heap, actually, I think Simon talked about this in his keynote. You can try to simulate that by just using let bindings in the right way in your rewriting. Right? So what we're going to do is we're going to reduce not exactly to the right-hand side, but we're going to introduce a let binding for the argument. And you do that basically for every function application and for every explicit let binding as well, but also for every function application, because the idea is that sharing applies to anything that's bound to a variable, right? And here we are having essentially a lambda, and so the enum from 2 is going to be used multiple times, so we're going to introduce a let binding for it and keep track of it. And now we want to reuse the x equals x, but because equals equals is strict in both arguments, so we need to evaluate it to the left and the right argument to weak at normal form. So we have to make progress on the x, right? So we do look at the x, and the x is enum from 2, 0, 2, and we reduce this. And then we already know that this reduces to that, right? So I'm skipping a couple of steps. Okay, and now we have to be careful again. But this is mostly, right, I mean, we have to be careful if we are trying to reason about what GHC is doing. Fortunately, GHC doesn't have to be so careful because it's already been written, that code. But, but if we now substitute, right, we're still not properly sharing. Because if we would substitute now the x, like what we've learned about the x to the right-hand side, we would duplicate the call to enum from 2, 0 plus 1, 2. And we don't want that. Right? So basically the rule is, if you want to do on-paper equational reasoning with lazy evaluation, informally the rule is you can only substitute a let binding if that let binding is a constructor that is applied to either values, like normal form values, or variables. Right? And here we have a constructor that is applied to an expression, to a complicated expression, to enum from to 0 plus 1. So we have to introduce another let binding, right, which is safe to do, right, just for this right-hand side of the cons. And now, right, we can kind of safely substitute the x and reduce the x equals x. And now this gets a little bit lengthy, but the let bindings are exactly the same. And now we just have, say, 0 cons x prime equals 0 cons x prime, and then we apply the second case of the equality function on lists, and we get 0 equals 0 and x prime equals x prime. Okay? And now there is an important point. And that is the big difference. That's probably why intuitively many of you thought this is linear space and not constant space. But this next step is the important point. Can you see what the important point is? Sorry, I heard the right thing, but I don't know from where. Yes, now x does not appear anywhere anymore. We have a let binding for x, but we don't need it. Right? It's not like the in is not mentioning x anymore. And x is not, so we can garbage collect it. Right? So we can do this step. And this is ensuring, right, that even though we have new allocations in every step, we can also in every step immediately free them again, just in time. And sort of the overall length, even in a long reduction, will always hover around the one that we're seeing on the screen right now, right? And now you can go on and reduce the 0 equals 0 to true. And then actually another thing where I've not shown the definition, right? But also quite important, the definition of AND does pattern matching on the first argument of AND, and not on the second, right? And the definition of AND says false and underscore equals false, and true and x equals x. So in this case, we can reduce AND without looking at the right argument to this. Okay, and now we can stop, right? Because now we can see that if you compare the first line and the last line, the only difference is that we have 0 plus 1, which is an additional suspension, but we'll talk about that in a moment. But it doesn't make a big difference. And basically you'll get the same steps again and again. So we have clearly linear time, but sort of the expression length will always be the same. So we have constant space. Okay? Good. Questions? Yes?
In this example, sharing of x isn't actually important.
In this example, sharing of x isn't actually important. Well, not for the sort of complexity class of the behavior we're getting. So if you were to compare, if you were to define sort of inline, say, self-equal and just write example 3 prime is 0.n equals 0.n, you would also get linear time constant space, right? But it still quite significantly affects the way in which you get constant space, right? And that's the reason why I've chosen this example. But yeah, you have a point. I mean, here sharing is not actually something that is beneficial, right? But this is generally, I mean, that's something to know, right? I mean, Sharing is most beneficial as a guideline, right? If the size of something is small, right, and the computation of it is expensive, right? It's actually relatively easy to understand that, but it's much less clear for things where the size is like sort of potentially large, like lists, right? Rather, as opposed to say an int or a double, right? And where the computation is cheap. I mean, so for something like 0.n is a typical example of something that very often you don't want to share. Like, I mean, if you are in a situation where you do use sort of ranges as iterators, and you have this habit of performing your own common sub-expression elimination, right? So any common expression, I'll just separate out into a where or a let. For these kinds of things, that can easily be bad, because, right, you can have a situation where you could stream, I mean, we haven't really been going to these examples yet, but you could stream the list very nicely, right, in both the use cases. But if you're sharing the list, then Haskell will want to retain it in memory, right? So it will then suddenly build the entire list into memory and hold on to it. I think this will actually come back in one way or the other in another example. But yeah, but it's a good point. Any other questions? Yes?
Can we actually observe the linear time in this equation from the runtime system?
Well, the runtime system is also giving you time. It's just that it is still so cheap that you probably have to go very far to get an actual indication of that it's linear. I mean, but so we can see that, for example, we have, what is it, 0.086 seconds total time now. And if I go by another factor of 10, you get to 0.83 seconds, which is a pretty good indication that it might be linear time, right? I mean, but it's nowhere near a guarantee. But you can clearly see that it's not constant time, right? At least that. Yes?
Yes. So we were having a discussion in the channel group. The question is the AND function strict?
The AND function. Yeah, so, okay, the question, okay, to repeat the question, is the AND function strict in the sense of strictness? So first of all, it's always a bit tricky to talk about strictness for functions with multiple arguments, because, right, you first have to agree what do you mean, and this is really what I mean. It's a sort of a convention, because there are two separate meanings, but one is perhaps not very interesting. If you're saying AND is a function in one argument because it's curried, right, then it is not strict, because if you are applying it to one argument, what you get is a lambda, right? And a lambda is not undefined. Like, even if you're applying it to undefined, you get a lambda, right? So you can. We haven't actually talked about seek yet, but you can see that in GHCI by trying something like AND undefined seek unit, and you'll get a unit. That's fine. If this would crash, this would not return unit. It would. But as I said, that's not a particularly interesting notion. What you typically say is that if a function has been applied to its arity of arguments, right, then how does it behave on each of these? And if you basically treat it as a function in two arguments, then you would say, okay, it's strict in its first, because the moment you apply it to two arguments, and it doesn't matter what the second one is, right? It will crash. But yeah, it is it's an interesting question.
So now we can talk about the definition of strictness, different definition for all these arguments.
Sorry.
So that we need a different definition of strictness, perhaps.
Yeah. So exactly. So the original definition of strictness is for a one-argument function, but you often want sort of a generalization for multiple argument functions, even though Haskell doesn't really have a notion of multi-argument functions. But it makes sense to talk about that, right? And it still makes sense because it's the questions that we're interested in. So yeah, I mean, don't get too I think it is important to know the definition of strictness simply because, it appears in the literature and but don't get too caught up on it for practical reasons, right? Because there are many other things. We should come to a break now soon, I think. We should do a quarter of an hour break. I'll take like one more question. Okay. The question is, why is AND not defined as a single argument function? That's actually a very good point. So you could define AND, and that actually now I need another 2 or 3 minutes, but I think it's a good question. So you could define my AND, bool to bool to bool, in this way, right? You could say X, I'm not a fan of lambda case, sorry. True, false, right? And now you could say, okay, right, if X is true, then, then it is lambda y arrow y, and otherwise it is false, right? That's, sorry, what did I do wrong? Const false. Right, something like this. That's a different definition of AND, and you could ask, why not this? That's, this one is strict, right? Like if I do the thing that I did before this here, my AND undefined. Now, oops, why does it? Oh, because I haven't loaded. Now this one crashes, right? Or even, I don't even need to do the seek now. No, I still do because of the show instance, sorry, yeah. Anyway, so it's a good question, but the point is that in general, right, I think the benefit you're getting from this is seen as inferior to the overhead that partial application introduces. Right, and so partial application is usually relatively okay in the sense that if you have a function that morally takes 5 arguments, right, and you apply all those 5 arguments, it will not by GHC be treated as a function that you first apply to 1 and then a second and then a third and then a fourth and then a 5th argument, but it will pass all those arguments at once, right? But if you and similarly, if you apply AND to 2 arguments, it will pass those 2 arguments at once. But if you define AND in this way, you actually have to pass the first argument first and then the second argument. So you basically lose that opportunity to pass all the arguments at once if they're all supplied. And I think that's probably the trade-off. Perhaps there are other reasons at play here, but that's what I would think. And there is perhaps another side to this, which says that if you define a function like you would define AND normally, like using 2 equations on 2 arguments, why doesn't it rewrite to this? That is exactly because it changes the laziness behavior, right? But yeah, it's a good point. Thank you for asking this. Okay. Well, yeah. Okay. Yes.
The thing about this is that if you compile with optimizations, GHC will lift out the lambda and make this strict, non-strict.
Will?
Yeah, unless pedantic bottoms.
Okay, yeah, you're right.
Can you maybe repeat it?
Yes. So actually, yeah. So GHC does actually. So GHC does actually perform these kinds of optimize. That's actually one of the points where GHC does do something like this. That's a good point. Yeah, I didn't pay attention to this. Yeah, and also I currently don't know which way around does it transform one into the other. Like, does it transform the original into this or this one into the other?
Make that function non-strict.
It will make that function non-strict. Okay, interesting. Okay. Yeah, so thank you for that amendment. Okay, so this is something where GHC is actually doing something which is perhaps slightly not okay with respect to strictness, but I guess it should usually not matter, and then there is a flag if you really care that you can prevent this. Okay, let's break for 15 minutes, I would say, for like reconvene at 5 past. All right, let's continue. Let me actually figure out where we were. Right. Okay, so we talked about sharing. So one thing which is a bit interesting, but it is in practice quite useful, also for some analysis stuff, is that if you have sharing at the top level, at the very top level, basically the top level of your module is like a let. Right, and normally if you have a let, you're expecting the bindings to be shared among the things in the body, but if you have something at the top level, then it's being shared basically across the program, right? It's shared everywhere. And that can be immensely useful, not in a situation like this, where you like do it just for fun, right, where I'm writing an artificially expensive computation, but this is something where you can easily observe this, even from GHCI. The first time I type expensive, it'll like wait 2 seconds until it has computed FIB32 or something, or on a faster machine perhaps 1 second, and be careful not to put a too large argument there. But somewhere in that range should be fine. And the second time it will be instantaneous, right? Because it shares the integer. And but I mean, the main use case for this is something like pre-computing certain tables, or there are memoization libraries that work essentially with this kind of trick, that you can memorize a function, and then the way that the memoization library works is that the function will actually not evaluate to a lambda immediately. It will evaluate to something which is essentially at its topmost point a table, which is shared among like the entire call of the program, and then the function will constitute lookups in that table. But of course, if you have potentially large shared computations over the lifetime of a program, or potentially the entire lifetime of a program, it's also potentially a recipe for introducing space leaks. But a side effect of this kind of stuff is that you can... was there a question? Yeah.
Do you know why it's called a constant applicative?
No. The question was, do I know why it is called a constant applicative form? No, I don't know. No, I don't even want to speculate. I guess, yes?
Just checking, did we actually say define what sharing means yet?
So there's a good point. We haven't been defining what sharing means. I wasn't planning to, but I can try. The idea of sharing, what's the best way to actually define that? I guess the idea of sharing is that you look at it in terms of a pointer, perhaps? I mean, so I don't know. That you...
So was an example where we had let x equals, and then this x is shared in the block?
Right. I mean... So conceptually, like, I mean, of course, if you're looking at it at the level of rewriting, then what we mean is that if you have been computing, like for a let binding, a result, right, then you want that to just use that result. I mean, the main effect is that perhaps I haven't shown the wrong thing first. Let me actually do that briefly. If we have a function like, say, f of x is x plus x, right? And now we do something like f applied to x plus 1, right? Now, if you do naive rewriting according to like reducing outermost redexes, then here, what can you reduce? Well, you can reduce f, right? And if we reduce it naively, we get x plus 1 plus x plus 1. And now you've duplicated work, right? And that's bad. So the idea of sharing is that instead you're doing let y equals x plus 1 in f of y, and then you're restricting the way in which you can do substitution, which basically says, yeah, I can only substitute if the variables are bound to constructor applications, which in turn are bound to variables if they have arguments. And y is currently not a constructor application, therefore I cannot reduce f applied to y at this point. Sorry, did I make a mistake? No. Yeah, I did. What is it? Y plus y, I should write. I cannot substitute y at this point and start and continue by reducing plus. So I have to first do this. Oh, sorry, perhaps I should also just say 4 plus 1 so that I can actually make progress here. And then at this point, now y is actually in the right shape, and now I can say 5 plus 5, and now I can say 10. Right, so that is sort of the rewriting view on it, but the memory view on it is simply we want to, again, like if we have multiple uses of the same variable, we want to compile them to things that point to the same memory location and only do the work associated with evaluating that memory location once. Does that help?
Yes, I guess informally, when the thing you're bound in that appears multiple times, you can say it's shared across the multiple
Yeah. So yeah, when the thing that is bound appears multiple times, then we say it is shared across those multiple uses. That's a good point. Yeah. And indeed, I mean, you don't really have to do that if something is used only once, right? You don't need to think about that very closely because then it doesn't matter. Okay, let's go back here. So there is we did lightweight measurement, but there is also something in GHCI which is a little bit instructive. I mean, I don't use it too often, but for educational purposes, it's certainly quite nice. So you can print a value in GHCI without forcing additional evaluation. And so there is this sprint, and there is a print command as well. And so if I type something like x equals, I mean, can even try to do it live. Let's do a GHCI session. X equals 0, ... 2 of type list of integer. Let's do sprint of x. So at this point, I have not evaluated anything. I can also make this a bit larger if I'm really looking at this. I've not evaluated anything, right? So x is just this computation, essentially this enum from 2 call. So that's why it just shows an underscore. Now if I try null of x, I get false. And now if I do sprint of x again, I see that in order to reduce the null, it had to evaluate x, and now because x is a constant applicative form, right? This is why this is relevant now, right? I can still look at x, right? It's bound and shared, but the other evaluation has like the evaluation of null has been triggering a certain amount of evaluation of the x, and I can now see that we know that the top level constructor is a cons, and we also know that the first element is a 0 because that is immediately following from the definition of enum from 2. There is no further computation, right? That is just inserting the first element into it. And actually there was like a question in the break, which is perhaps something that I could even forward, because if I do something like, let's say, take 1 of x, let's say null of drop 1 of x. So I drop one element from this list, and then I check whether it's null. That should also be false, right? Because, I mean, modulo laziness, I'm getting the list 1, ... 2, and that is clearly not empty. But now if I print x again, what do you think it will print? Yeah, slightly more, but how much exactly? 0 cons 1 cons underscore. That's what you expected? Why not 0 cons underscore cons underscore? Is it a question or answer?
Answer, I guess.
Okay, answer.
Probably because the enum instance for int knows that incrementing ints is cheap, so it can do that strictly before returning a const.
So the answer suggested was that because the enum instance for int is probably sort of, let me rephrase or paraphrase a bit, efficient, defined in an efficient enough way so that it knows that it can do that strictly. That is true. I mean, that is actually true, and it is defined in this way. It uses sort of unboxed integers under the hood and doesn't even do the laziness thing. But even if I don't want to spend the time on that, but I've tried this before. Even if we would use our version of enum from 2, it would still print this. Why? Yeah, or is that answer or question?
We have this if condition in the definition, right?
Yeah.
On this incrementing number.
Yeah.
So we need to inspect the number to see if it's...
Yeah. So the answer is that if you look at the definition of enum from 2, it's unfortunately quite a bit back. Let me see. Where did we have it? Here. Right. Here, you see that if you are entering enum from 2, the first thing you have to compute is L is greater than U. Right? And that is an operation on 2 integers and will force, in order to reduce this if then else, right, we will have to compute L and U. So basically, whenever we get into the situation that we can construct the L cons, we know what L is. Right, even in this one, so it's always going to be an already evaluated integer value, right? But there are lots of interesting things you can do with this print and sprint. There is a question, yes?
What is the definition of sprint?
So the definition of sprint. Sprint is a GHCI command. It's not a Haskell function, so it's a feature of GHCI. Or are you asking why it is called sprint? I think the S is for simple because there's also print. So let's just very briefly look at that. But there's a minor difference. So if we do print instead, it's actually giving a name to the unevaluated expression, which you can even use subsequently. That can sometimes be helpful. It's even brought into scope, and then you can do further evaluations on that one in order to analyze it further. That is the main difference. There are lots of interesting things you can do with print and sprint, and you can play with it. There are a couple of shortcomings. One significant shortcoming is that it cannot deal with cyclic structures. So if you do x equals repeat 1 and then print x, that's still fine. But now if I do something like, I don't know, I think head is even enough. Null is even enough, null x. And then print again, then it will just hang. It will not recognize that because there's a cyclic pointer structure, and it's not traversing it in the right way. There are other tools like GHC debug can do this, GHC heap view can do this, but you need to go to a slightly different level, and print and sprint unfortunately can't. I think it would be nice if they were extended so that they can, but that's the reality at the moment. Another thing that is a common pitfall if you do this in the first time in GHC, if I do something like this, I get this, right? Now you can already see the type signature, but sprint will just print an underscore. Sprint is even more dangerous. I think print in that sense is better because it warns you effectively. But now if I do null x, I get false, and if I do sprint x, I still get the underscore. Why is that? Yes?
Dictionary.
Yeah. So it's So the answer was the dictionary. So I think it's an interaction of multiple strange things in Haskell, right? So there is a thing called the monomorphism restriction. Who has heard about that? Right. So the monomorphism restriction, there's actually a good point in favor of the monomorphism restriction, right? So it's one of the main reasons why it was introduced in the first place is that you might write something like x equals bracket 0.10 somewhere in your Haskell program, like in a let binding, and expect it to be a shared list, right? But what it is in practice, at least without the monomorphism restriction, is an overloaded thing. So, right, because you can see that at the type here, it's actually of type num a, enum a list of a, right? Because integer literals are overloaded, right? So the only thing we need to know is that the thing in the list is a num class so that we can use these integer literals, and there's in the enum class so that we can use the ... But otherwise, it's unspecified. And the way this is translated is to a function. So x is effectively a function that takes an implicit argument, or even two implicit arguments, depending on how you want to look at it. The num a and the enum a dictionary for the type that you're eventually using, right? And now another thing comes into play. So the first thing is GHCI since version 7.10, I think, or something along those lines, does not enable the monomorphism restriction anymore, right? So you actually get the overloaded type. If I write x equals to, what is the type of x? I get num a double arrow a. If you do the same thing in the Haskell module, you get integer. Because first, monomorphism restriction, top-level binding without any arguments cannot have an overloaded type. Second, defaulting. If that overloaded type involves a num constraint and some other strange conditions, then it will default the thing to something, and most of the time to integer, right? So that's what normal Haskell code does, but GHCI behaves differently. I don't want to rehash the entire arguments in favor, I think, but it leads to confusion sometimes, right? So that's the first thing to keep in mind. But then there is another thing which is also a difference between GHCI and Haskell now, because we are doing a call of null to x, right? And why does that succeed? Because now we have unresolved overloading, right? We're applying null to something which is overloaded over the num and the enum class. And there, like in order to see which implementation do we have to choose, I mean, we have to fill in the dictionary argument somehow, right? So how does that work? Well, by another difference between GHCI and normal Haskell, because there is something which is called extended default rules. And GHCI will essentially not just default num constraints, but any constraints to unit if it can. I think in the case that it's a num constraint like here, it may actually still pick integer. I think it probably still picks integer here because there is num involved. You can do that by enabling warnings. Let me try this again, just to see. Yeah, now I get a shadowing warning, that's fine. Then let's do the null x call. Yeah, so it defaults to integer. So in this case, we're not even using the extended defaulting rules, but GHCI will default a whole lot, right? And the motivations for that are more clear. I think the main motivation for extended default rules is that if you just type the empty list into GHCI and you didn't have extended defaulting, it would cause an ambiguity error, as you can see by the warning here, because in order to show the empty list, you have to know the type of the element. And so you would have unresolved overloading, and that is also not very satisfactory. Okay. Anyway, so you have to watch out with this sort of stuff, because now if it's a function, right? If it's effectively a function, and then we do null on the function, then the function itself does not get evaluated any further. And it's another artifact of sprint and print that it prints functions always as underscore, which is also not good. If you use like a proper heap analysis tool, it will tell you what kind of heap object it is, and you can see that it is a function. But yeah, that's something to keep in mind. Anyway, that is all a little bit of a sidetrack. So let's get back to wherever we were. Yeah, sorry. Yeah, here. Let's look at this, which is, again, just a small variation on the theme, but the new thing is that we have introduced a map call. Right? So we are generating the list, we're mapping over it, and then we're checking whether it's null. So, old question, constant space or linear space? Who is in favor of constant space? Quite a few. Who is in favor of linear space? Very few. Okay. Again, we have to, like, if we reason about it, we can measure, right? And I think I can just to save time, this is constant space. This is still constant space. If we measure it, it is still constant space. But why, right? We still have to look at the definition of map. We have to perform our reasoning. It's as normal. There are parentheses missing here. Sorry for that one. So there should be extra parentheses around enum from to 0 to, though that reduces in a way, and now there are parentheses missing again. Sorry, yeah, that's due to like not properly doing this highlighting thing in my LaTeX sources. That's actually responsible for that. So then the question is, can we reduce this call to map, right? And if you look at the definition of map, you can see, again, we perform pattern matching on the list. We don't perform any real pattern matching on the function. So if we take sort of this slightly relaxed view, the function map is strict in its second argument, but not in its first. So we can, after we have reduced enum from 2, we can reduce map. And then we get this. We get null applied to 0 is less than or equal to 10 cons a recursive map call, where again there are parentheses missing. Sorry for that. And at this point we can reduce null, and we get false. Okay. So that's, I guess it's makes it relatively easy to see that this is still constant space, and actually also still constant time. Even it just introduces another indirection. And I think this is actually. Even though you can argue that there are optimizers and so on and so forth, but this is the main reason why I think laziness is really great, right? That you can build these kinds of pipelines, and whether they are on lists or on other data structures does not really matter, right? I mean, even if you say have a tree structure and you map over it twice, right, of course it's going to be less efficient than mapping over it only once with the composition of the function, but it's not going to be substantially less efficient because like you're ultimately consuming your data structure in a particular way, and you're not going to build the whole intermediate data structure, right? This kind of composition sort of is naturally relatively well behaved in a lazy language, which in turn encourages composition. Right? That's the main point. I mean, the whole point of functional programming is that we want to compose things out of smaller things, and the somewhat unfortunate aspect of eagerly evaluated languages is that every time you use a composition, you build an intermediate structure. So while it's conceptually a nice thing to do, in performance terms, it's usually not a nice thing to do. So we also often, I think, see with people who are programming in eager languages that they use this for designing a program or for reasoning about what it should do. But then when it comes to production time, rewrite to a monolithic loop, because that is just more efficient, right? That's totally understandable. But it's pretty nice that in Haskell these kinds of things work. And of course now for lists, there is to be said that there is a whole framework based on rewrite rules that tries to make it even more efficient, right? That if you enable optimizations, you'll have like all these rewrite rules that exploit something that is called fold our build fusion, and try to remove all the intermediate structures completely. But the point is that is sort of a gradual improvement. Right? It doesn't change the complexity class. Even without optimizations, you get the same complexity class. It still like perhaps lowers the factors quite a bit, but you don't really need it. And it also means that you're still going to be worse if you define your own list data type or your own variants of list data types and so on. But you're not going to be substantially worse, right? So in that sense, I think that laziness is being bashed so often. I thought I would just try to really think. I think it's a good idea, right? I think it makes a lot of stuff harder, but it also makes quite a lot of stuff easier. And it is sometimes like if you're working in a lazy language, then obviously you're annoyed by the shortcomings of laziness. But sometimes it's hard to see all the things that you might be gaining. Okay, so let's try to look at a variant of this example, and rather than map, we have reverse. Now, again, I guess the only viable contenders are constant space and linear space. Let's do this. Yes.
How's reverse implemented here?
Choose your definition. Like, I mean, you can try to implement it however you want. Or I don't know. Correctly. It's implemented correctly. No, I mean, let's say with the actual JHC definition of reverse. Okay, so who is in favor of constant space? Who is in favor of linear space? Okay, so majority shift. This time the majority is right. So let's see. All right, I mean, this is effectively what the definition amounts to. This is not exactly the definition that GHC is using, but I think it's pretty close. So an accumulator-based reverse definition, you can make it much less efficient by defining it in terms of plus, but that won't make the space behavior will it? I don't think it will make it yet worse. But in any case, this is a reasonably efficient definition. So basically, you're having an accumulator, you're traversing the list, and you're just moving, right? While traversing the list, you're reversing. You're just moving things like elements onto the accumulator, and by moving them from one pile to another pile, you're reversing the list. And when you're through, you're returning the accumulator. Okay, so now if we do equational reasoning again, we see it starts pretty normal, right? We get to the point where we have reduced enum from 2, so that we have revealed that there is a 0 at the top of the list. Now we shift that over to the accumulator, so the accumulator is now 0 cons nil, and we have the recursive call, but we are still nowhere close to reducing null, right? Simply because we know nothing about the result. And really, we don't know anything about the result until we have traversed the entire list, because that is the moment that we are returning the accumulator. And then we can immediately reduce null. But here, we have to evaluate the entire, traverse the entire input list until we get there, and build an accumulator that has the entire reverse list in there, and therefore that's the case. I mean, if we really had a list that has unevaluated elements, I mean, enum from 2 generates them in evaluated form, as we have already discussed, but reverse would not force the evaluation of the elements of the list, right? It would leave those alone, but it would still create linear space because the spine of the list has to be realized. Okay, so we have linear space. Now, okay, so the difference between the 2 examples, map and reverse, was just the function in the middle. We have generation, a function, and then null. Why does one of them work or do good things and the other do bad things? What is the property? Yes? Sorry, I didn't quite get it, but okay. Let's do another. Yeah.
So map immediately returns a constructor.
Mm-hmm. Yeah.
So it's tail recursive.
Okay, so now we have two different answers, and that's actually good that you mentioned this. So we have. So one answer, your answer was map immediately returns a constructor. That is actually good. I mean, that's a good answer, but it's also like a really good property, right? So if you look at map, you do a pattern match, and then on the right-hand side, in the first case, you produce nil, and the second case, the outermost thing is cons. Right, so you they immediately produce a constructor, and that's a very good property for a function to have. Sometimes this is called guarded recursion or guarded co-recursion. So in Haskell, this is great, right? Because it means that when we have made a reduction, we're immediately in weak-head normal form. And if we're immediately in weak-head normal form, there might be other things that are waiting for our result that can already continue. We might not need to do anything more, right? So you said it's tail recursive, and that's not the case, right? And that's actually an important point. Map isn't tail recursive because tail recursion is weird in functional languages. It has nothing to do with Haskell because it doesn't actually really look like anything to do with the tail, right? You have to look at continuations or evaluation contexts, as Alexis talked about this morning. The point is, it looks here like syntactically map is in tail position, right? But actually there is an evaluation context around the call to map, and that is the f of x cons. That means after map returns, there is still stuff left to do, namely to put it into the cons. But because we are doing lazy evaluation, that doesn't matter at all, because we first produce the cons, ask other people what they want to do with this, and someone else has the job of actually even forcing the map call, so we don't care about this. Tail recursion is a very, very important property in eagerly evaluated languages, and it is still relevant in lazily evaluated languages like Haskell, but it's not the one and all, right? There is this other form of recursive pattern, this guarded co-recursion, which is equally good, or even better in many cases, right? So don't think that anything you ever writing has to be tail recursive. But also, just to complete that, to recognize that something is tail recursive typically means then that the outermost call to the function, to the recursive, the outermost call is a recursive call, right? So, and we'll see an example of that in a moment. Okay. Yes. The question is, does that mean that tail recursion and weak-head normal form are mutually recursive? And the answer to that is yes, because something is in weak-head normal form if it's a constructor application. Mutually
exclusive instead of mutually recursive.
Sorry. Nevertheless, yeah, sorry, but nevertheless, I think I understand. It's mutually exclusive, because if something is in weak normal form, it's a constructor application, and then in particular, it can't be a recursive call, right? Because a constructor is not a function. Yes. Okay. All right. So this is the point, and I mean, often I'm informally calling this property incrementality, right? So that's another way to look at it. You can produce results incrementally, like without evaluating the complete input list, we can start producing parts of the output list. That is a good property that map has, and reverse doesn't. If you want to evaluate the result of reverse, even just to weak normal form, you have to already traverse the spine of the entire input list. Yes, Bartosz?
So if you use the naive definition of reverse,
yes. Yes.
That will work better?
The question is whether it would work better if I used the naive definition of reverse using ++. The answer to that is no, it would not work better, because it's still the same. If in order for you to know that the first constructor or the outermost constructor of the result list is a nil or a cons, you still have to effectively traverse the entire input list, also in the definition with ++. You have to actually perform far more reductions to actually get to that point. But I mean, if you look, if we just do this, if you do reverse of, say, 0, let's even just say that this one is already evaluated, okay? And we define it naively, then we get something like reverse of 1 cons, 2 cons, the empty list ++, 0, right? That is the naive definition. Now you have a call to ++, right? And in order to know what ++ does, you have to look at the first argument of ++, and that is another call to reverse. And now you're in the same situation, right? So you won't know what the first constructor or the outermost constructor that this ++ call returns is before you haven't done all the recursive reverse calls. Yes?
Even if ++ was recursive in the second argument?
If ++ was recursive in the second argument, the problem with ++ being recursive in the second argument is there, I think, no useful definition of ++ you can give if it's recursive in the second argument, because unless you make ++ itself somehow reverse the list again, right? There is simply nothing by looking at the second argument to ++ that you can say about the result. Yeah, I think that doesn't help. Okay, so we have to see. We go on. Let's actually skip about this. It's an exercise you can do on your own, like which of these functions should be incremental, and look at another example. Let's look at length. Okay? So let's change the definition of null once more, and let's define null via the length function. And let's say null is now defined to be that the length of excess is equal to 0, and then we're checking null via length of 0.n. Again, constant space, who's in favor of constant space? Oh, at least one. Okay, who is in favor of linear space? Okay, yeah, good choice. So intuitively, let's actually do first intuitively, because I want to go a little bit into different ways to define length, and probably that will be among the last things that we can cover. But but intuitively, why is it linear space? I mean, even regardless of the definition of length, or the exact definition of length, why will it have to be linear space? Because the equality is on numbers, right? And the equality on numbers is, again, strict in both arguments. That means we have to know both numbers, and so that means we have to have an actual number Not just some sort of information, it's not 0, but we have to have an actual number, and if the other length is 1,000, then we'll have to compute that 1,000 before we can reduce 1,000 equals 0. At least if it's done on integers, right? Haskell is like, in principle, you could define number types that are lazy, right? That's a whole different topic, which allow something like if you do which is not very efficient for other reasons, but if you define something like piano naturals, then you can define a sort of a lazy form of equality where you could reduce this more efficiently or something like that. But then you would have to use generic length and not length, or perhaps not even that is enough. I have to check exactly what the class constraints is. But it's an aside. There was a question, yes?
Does this make the space usage actually linear? Because we can again garbage collect kind of as we reverse the list in this case.
Oh, did I make a mistake? Let me see. I think you are right. I think this is just me getting tired. Yes. Very good. Very good. Let's measure before we get even more confused. So let me not. Let's do example 5 briefly. Why is it not in scope? Because it's different versions of length, but I think the built-in length is here called example 5a. That's the, let me see. Let's do back to, let's just do all examples. And then, so that was my mistake. Sorry for that. Yeah, because I was ahead of myself, or because in the talk I'm immediately jumping to the definition of length, and I got kind of. But these kind of things happen all the time. But you made exactly the right argument. Sure, we have to traverse the entire length of the list, right? So in that sense, it is clearly linear time. But we can garbage collect immediately because there is nothing that forces us to retain it. So even while we are evaluating, we can always get rid of it, right? But it depends on length being implemented in a good way. And actually, this is perhaps many of you have seen this before, but it is such an important point that is probably worth reiterating. So if we just look at different definitions of length, and I have to be relatively quick now because we are already near the end of the lecture, but I kind of hope that many of you have seen this part before. This definition of length is probably sort of the one that somebody who's just learned Haskell would write, or at least I would actually be happy if somebody who has just learned Haskell, the first day of Haskell, would write this definition of length. Because why? It's very systematic, right? You do pattern matching on the list, you follow the structure of the list, you make a recursive call to the tail of the list, not being afraid of recursion, very good, and it's very systematic and straightforward, and unfortunately it doesn't work very well. Why does it not work very well? Because if you do equational reasoning, you get to the point that you're reducing length of 0 cons enum from 2 to 1 plus the length of something, and now 1 plus is not reducible, we have to go on with the length, and then you reduce that again, and you get 1 plus bracket 1 plus something, and we can still not reduce anything. It's just 1 pluses that are all bracketed the wrong way, right? Because you're sort of traversing the list and building all these increments by 1, but none of these can be reduced until you're all the way through the list, and then you have 1 plus 1 plus 1 plus 0, and then you have this inner 1 plus 0 finally that you can start reducing, and then you can collapse it all the way down to 3 again. So this version is linear space. This version is linear space. And sorry, I mean, I think I even said wrong things again. Yeah, 3 hours is too long. This version is linear space is correct, but just what I just realized is that I was making this point about the garbage collection before, and that is just nonsense, right? I mean, there is not even so much about garbage. Well, the list itself can be garbage collected, but length doesn't need linear space in the first place. Yeah. So if that was still confusing, then hopefully these versions will make it clear. So this version is bad, right? And it is linear space. But you could think you can fix that by switching to a version that uses an accumulator, right? And if you do that naively and run it without optimizations, right, it is still not going to be better. Why not? Because now, if you're at the point where your accumulator is 0 and you have a list starting with 0, you want to increment the accumulator, but you're incrementing it to the computation 1 plus 0. And then the next time you're incrementing it to the computation 1 plus 1 plus 0. And nothing demands us to know the result here yet. Really only when we've reached the end of the list, we return the accumulated suspended computation and then can reduce it, and it's still linear space. Okay? And this is, yeah?
Why can't you reduce the accumulator in the middle?
Oh, we can reduce the accumulator, but why would we if we are following the strategy that we have been determining so far, that we are always choosing the outermost radix? The outermost radix in all these lines is the application of length ac, and we can reduce that. So we don't reduce the other, but we could. We could, and actually that is the solution. We just have to deviate from the standard evaluation strategy. We have to artificially place demand on this accumulator. Yes.
And on the preceding one, you cannot use the associativity of addition.
Oh, the question is, can we use the associativity of addition? Well, that's an interesting question. I leave that to you as a research topic. I think in principle it is conceivable that you could do some sort of automatic rewriting and using associativity of addition, but in general this is not the kind of stuff that Haskell does. Haskell doesn't even know about whether functions are associative or not, and it certainly doesn't take such properties into account usually in code generation. But if you have a system where you can reason about such features, could it perform rewrites like that? Yeah, sure, possibly it could. Would it make things overall better? I don't know, but yeah. Right, so the solution here, and this is really one of the common points where this is becoming relevant, is that we can fix the problem by making length ac more strict. Right. So, and how do we make it more strict? By using a bang pattern. And the bang pattern is something where you can think of, it's basically only matching if the argument is in weak-head normal form, even though there is no constructor visible. Right, there wouldn't be a good constructor we could match on for int. What would we match on, right? We could make cases for, what if the accumulator is 0? What if the accumulator is 1? What if the accumulator is 2? But that would be very inconvenient. But instead, we're just artificially saying, okay, only match on this if the integer is in weak-head normal form. And that has the desired effect. That means that now, in the reduction sequence, at this step, which is the critical step, we cannot reduce length ac. We have to first, for it to match, right? We have to first put 1 plus 0 into weak-head normal form and do this reduction. And now it's fine, right? Now we basically get the desired thing without having this. And now length runs in constant space, and therefore the original example runs in constant space. And sorry for the confusion there of first saying the wrong thing. But this is really, this is a pattern where these bang patterns are really useful in practice, right? For accumulators. And accumulators, to me, are things that you don't need until much, much later, right? You build them, but you don't use them yet, and only later you return them. That is sort of the thing that should trigger. That is the main place where you often have to help, where you sometimes have to place artificial demand, and that is a good point. So there are a couple of things. So I think I agreed with Jasper that I could go until something like 10 past or something like that. Yeah. I think there are a couple of things we should still talk about with respect to bang patterns. But there was a question. Yes.
My question is, like you mentioned, actually, that with some optimizations, this probably naive accumulator will still be probably optimized to basically automatically bang or not. Can I extend?
Yes. That's okay. So let's actually go to that first then, because that's another thing that that I have here. So the demand analyzer, which we already talked about, will optimize, if you enable optimizations, will optimize the sort of the version of length written, the non-annotated accumulator, to the version which has the bang pattern. That is something that JHC will be able to do, because it can determine that in this definition that we had, which one is it? This one, that the accumulator is always going to be eventually used. Right? We can walk through that, and that actually, I talked about this during the break as well. This is one of the points where this notion, not all notions of crashing and diverging are equivalent, is actually pretty useful, because the point is, in order to make the case that the accumulator will always eventually be used if you use the result, right? That point depends superficially on the first case being reached, right? Because if you can guarantee that the first case is being reached, then you use the accumulator. It's like at the moment you demand the result, it is the accumulator. But what if the first case is never being reached, right? Do we then use the accumulator? No. Actually, if you feed length an infinite list, the empty list case will never be reached. But the point is, in that case, the function will loop, right? And the loop is equally good as a crash, right? And that's why you can assume that it is always using the accumulator, and that's why it's safe to make the accumulator strict, right? So that is one of these scenarios. So, but should you rely on the demand analyzer? That's perhaps another good point. I think not, and perhaps this won't convince you, but in general, it is often very easy to write correct definitions of functions that nevertheless don't work for the demand analyzer. And you just have to make a relatively small modification to length so that the demand analyzer won't optimize it, because it's correct not to optimize it. If we simply replace the case for the empty list with 0, this is a little bit tricky, but the point is we're only ever reaching the empty list case if we're calling it with the empty list in the first place. That is our internal argument. And then we make the base case the one-element list, in which case we return 1 plus ACK, and we keep the recursive case as it was. Now, in the empty list case, we're not using ACK, right? And now it's not safe to make ACK strict. And so in this particular example, I don't think anybody would write length this way, except perhaps sort of within their first days of Haskell, where many people seem to be tempted to like use extra cases when they're not needed, but later on perhaps not so much anymore. But in general, I think there are often like tricky things at play for function definitions, and it's better if you know. It's better to make an annotation. At the same time, I would also not stress too much. I think the general idea is to keep things manageable. Don't sprinkle bang patterns everywhere. That's not a good idea. Think very carefully about where they are needed and why they are needed. The general idea is that in most cases, right, you should apply strictness and variance to your data types, ideally. Like that you're saying that like this data type will always have these things evaluated whenever it is around, and then the functions that operate on those just have to maintain that implicit strictness invariant. Basically, accumulators are one of the few things where you sometimes have to put such annotations on functions, and in my experience. Okay, so now the question is what to do in the final 5 minutes, possibly just to answer more questions and conclude. I want to perhaps briefly sketch a few things that are still left, and perhaps we can do like sketch one of these. So I have a couple of pitfalls for bang patterns and seek. That is still in this part. And then I have like 3 more examples, which we won't get to, but 2 of them are connected. And perhaps it's actually nicest to still briefly actually use the final minutes to still look at this one, to just like and actually look at the 7, like the variant which is worse, let's say. So what about this example? Like sort of as a final question, we're using partition. Do you know partition? Partition is a bit like filter, right? Only that it doesn't just retain the things that pass the test. It retains both the things that pass the test and the things that fail the test, and builds a pair of 2 result lists. So here we are partitioning using the even function that checks whether a number is even, the list from 1 to up to n. And then we're getting a pair, and then we're summing all the even numbers and all the non-even numbers. What do you think?
It's linear space.
It's linear space.
Because we cannot garbage collect. We cannot garbage collect during the first sum.
Because so we cannot garbage collect during the first sum, yeah. So I will try to like appeal to intuition here. The slides are available online, but walking through the slides will just bring us vastly over time. But the problem here, and I think it's right what you said mostly, or at least the way I understand it, is that we're building a pair of lists, right? But the generation of these lists is connected, it's not independent. We're not building one list using one generator and another list using another generator. We're building these 2 lists from the same input list. And the distribution between these 2 lists is dynamic. So we don't statically know at compile time, I mean in this case because the input is completely clear, but in general, if we use partition even and we have an unknown input list, we don't know like when will something go to the one list and when will something go to the other list. And in this situation, we have no chance of consuming this in constant space. Because if we look at the one list first, then while reducing the first list, the other list will still build up in memory as an unconsumed thing, right? There will still be uneven numbers while we're looking at all the even numbers and continuing processing them. There will be uneven numbers that end up in the other list, or odd numbers, sorry. And if we look at the odd numbers first, then the same thing will happen with the even numbers. And if we not somehow accidentally consume them from both lists in exactly the order that they're inserted there will always be a leak. Right? So there is simply no chance that we have. And that is an important realization. That's another quite common pitfall for functions such as this, that they're inherently leaking, right, if you're doing this. And actually, the better way to write something like this, right, because the better way to write something, which is also explained on the slides as a strategy, is to tag the elements, right, to say partitioning is essentially, I don't know, conceptually you could say map a function over the list that if the predicate is true, turns it into a left of an integer, otherwise it's a right of an integer, and then fold over it once with a pair of accumulators summing up the two totals, and then everything is fine, right? And you can restore modularity there as well by using some streaming libraries or a library such as fold-L by Gabriela Gonzalez, right? There are good options there to also make it elegant again. But it is a problematic type, right? It's a problematic type. The pair of list of int. It's not always problematic, but it is problematic if these two lists are coming from the same source, right? And that is something to keep in mind, okay? And sorry, perhaps as a very final remark, there is another problematic type, that's the last example, which is basically about traversals, which is also inherently problematic. And that is like if you have a type such as maybe of list of integer. If you don't even have to look at this example. Just consider maybe of list of integer is an inherently problematic type. Why is it inherently problematic? Because most of the time, I mean, except perhaps in the special case, you know upfront whether you fail or not, right? But if you can fail during list generation, right? You generate the lists, but you can fail at any point in time, then maybe list of int is not the type that allows you to express that in constant space, because maybe forces the choice between failure and success to the very top. And so in order, before you can even inspect the very first element of the list, you first have to traverse to the end of the list to ensure that there has not been any failure. So just like you should always feel a warning light go up if you see something like pair of list of int, you should also feel a warning light going up if you ever see the type maybe of list of int. It's not saying that you should never use it, but you should definitely ask yourself, do I know how large these lists are? Is it really what I want, right? These kinds of questions. And that's perhaps a good point to conclude. And you can still look at the slides and you can still ask me questions, but I think we should stop to get the room free for the next session. Okay. I mean, perhaps one or two questions, or is that still okay? Or yeah. Okay. I saw some hands. Yes.
So you mentioned a pair of accumulators. By that you don't mean a lazy tuple of two accumulators.
No, I mean, so as I said, there are many things that I did not talk about. So another common pitfall with these bang patterns is, of course, and we didn't talk about that in very much detail, that they force the argument to weak head normal form. And one of the most common mistakes in practice is that like if you then feed a data structure in, such as a pair, right? A pair is in weak head normal form the moment you produce the pair constructor, right? So if you force a pair to weak head normal form, none of the two arguments get evaluated. So in such a situation, you then have to either use a sort of nested bang pattern, where you match on the pair and put bangs on the two component, or a data structure that has two strict, like bang annotated fields. But yeah. Was that your question? Or yeah, okay. It doesn't really, but that's a good point. The original example for the partitioning was using greater than or equal to 0. That's the which I also skipped over. And this is chosen in such a way that you basically expect almost all of the elements to go into the first bucket. And if you can expect that, then it is relatively okay, because then if you are also looking at the first list first, you will not build up an uncontrollably large thunk in the second one. But if you decide to look at the second component first, you still do. Right? So it is still very tricky. So the only difference here is that here you basically kind of statically know the distribution, and therefore you have a chance to consume it in an order that doesn't produce a problem. Whereas in the other, you clearly don't statically know the order, and you don't have a chance. But both are very critical and very dangerous, right? And another thing which is also mentioned on the slides is that writer, the classic writer monad, is essentially an instance of this. Like, never use writer because it has an inherent space leak, right? Sorry for just dropping this as the final sentence if this is the first time you hear about it, but it is essentially an instance of the same problem, because writer is a pair between the log you're creating and the result you're actually interested in. And you have a dynamic distribution between when you're adding to the log and when you're adding to the result, and you're basically running into exactly the same problem. Okay. Thank you all very much. I'm still around tomorrow, so and today, of course. So if you have more questions, just find me. It was nice that so many of you were here. Yeah, thank you.